Okay, so the first one. So why do you think ammonia has a higher boiling point?
It has hydrogen bonding, I think.
Okay, so that's fine. That's perfectly fine. Hydrogen bonding is one of the strongest intermolecular forces, and it has that. Now, neutrons are passed through an electric field. Mass of one neutron is 1 over 12, the mass of a carbon 12 atom. And any deflection in the electric field is recorded. So the neutron and the carbon 12, he says that the mass of a neutron is 1/12 the mass of a carbon 12, right? I mean, talk about mass. And any deflection, which row is correct? So the mass of neutron, what is the mass of a neutron?
1.
Yeah, that's pretty obvious. And behavior in electric field.
It doesn't deflect.
Okay, so I don't know why they gave this. I mean, it was a pretty straightforward question. As a table refers to the electron distribution in the second shell of an atom with 8 protons. 8 protons. So which row is correct for this atom?
Okay.
Second shell electron distribution.
Second shell. So it's supposed to be 1s2, 2s2, 2p4, right? So second shell, it's S, and it has 2 electrons, and then first one it's P. The dumbbell shaped is P.
Okay.
And it has more electrons. So it's B, yeah.
Okay. Which statement describes the bond? So the bond between carbon and hydrogen in an ethene molecule.
It's between carbon and hydrogen, it's a sigma bond.
Yeah.
And it's sp2 because it's double bond.
Okay, so it's double bond and yeah, that's fine. sp2 and this one, right? Now this one is you need a calculator for this. There's aspirin, the MR is given, can be made by reaction between 2-hydroxybenzoic acid. So this is 2-hydroxybenzoic acid and ethanoic anhydride C4H6O3, which is this one. And it forms aspirin, which is this. And the balance equation is given. If a reaction consists of 10 grams of each of the two reactants, so you got 10 grams of this, and you got 10 grams of this. What is the maximum mass of aspirin that can be produced?
So we have to find the number of moles, and one of them is in excess. So we have to find the number of moles of each, and
so
I need my calculator.
Okay.
Yeah, I got my calculator.
Okay.
Okay, so number of moles of the 2-hydroxybenzoic acid, it would be mass 10 grams over the MR.
So
The MR is 138, so it's 10 over 138.
Yeah.
That is 0.0724. And for the other one, the MR is 4 times 12, just 6.
It's given, it's
The
100.
MR is 102. Yes. Oh yeah, it's given. Okay. So it's 10 over 102. Okay, so that means that the C4H6O3 is in excess.
See,
Right?
what do you get for this? The second one?
0.098.
Okay, so that's an excess. So you never use the excess moles, right? You're going to use the limiting.
So that's the same number of moles. And they gave the MR as 180, so the mass would be number of moles times MR. So that's 0.0724 times MR.
Okay.
That should be 13C.
Okay, so that's C. Then a which diagram correctly describes the behavior of a fixed mass of an ideal gas?
Yeah. At constant temperature, when volume increases, pressure increases, that's wrong. B is wrong.
Yeah.
And okay. How do I, is this like memorized?
No, it's just you see you got this. This is your ideal gas equation, right?
Yes.
So based on that, what about the first one? Option A, is that wrong or right?
When pressure, I think is it A?
Volume and temperature, right? So volume and temperature, that's they are directly proportional, right?
Yes.
If the others are constant, right? The pressure is constant, right?
Yes.
So pressure is constant. The moles are constant as well because it's a fixed mass, right? And the
Yes.
temperature is also constant. So that's fine. A is perfectly fine. You have problem with this one, right?
Yeah.
So over here he's plotting PV versus P, right? So what do you think? And temperature is constant, right? So what do you think
Con-
is the value of PV if the moles are constant because it's a fixed mass? R is already a constant because it's obviously a constant. And he said, I mean, this case, right? And he's saying that T is also a constant. So if all of them
So
are,
it's supposed to not change.
yeah,
It won't increase.
it should be a straight line, right?
Yes.
And the same, I guess, in the second one as well, because PV, the value of PV will not change because yeah, it's exactly the same. It's constant T, right? So moles are constant,
Same
R,
moles, same temperature.
yeah, so that's going to be a constant as well.
Okay,
So
I got it.
and also remember that since you don't know about this, Tika, I'm just going to briefly tell you about this specific graph. So a few things. One second, let me open this. Actually, we can. So remember PV versus P. What happens in it is that uh, PV versus P or PV versus V, whatever it is. So what happens in it is it's going to be a constant, right? You understand the point, right? That it's going to be a constant if temperature is constant, right?
Yes.
So you've got PV is equal to nRT, and these three are
Yes, ma'am.
constant. Yeah, and so you get a straight line, right? ठीक है अयान आवाज आ रही है चलो अच्छा सो
जी
दिस
सर
अच्छा तो बस ये रेगुलर इसी टाइम पे हो रही होगी क्लास ठीक है अच्छा now so this one PV versus it's going to be a constant right now the idea is that if you have an ideal gas if pressure increases so whenever you have an ideal gas what happens is that if pressure increases what happens to the volume it decreases right
Decreases.
so but the product is going to be a constant or vice versa because they're inversely proportional right vice versa is that if you decrease pressure the volume will increase, right? But the product would
Yes.
remain a constant. So it doesn't really matter what pressure it is or what volume it is, the product is always going to be a constant. Is that clear? Because pressure and volume are inversely proportional and one increases, the other decreases, the product remains a constant. Okay, so Judy, is this clear?
Yeah, it's clear.
Now what happens is what the next thing is that for a non-ideal gas, the graph kind of looks like this. He gets because the problem is the non-ideal gas does not obey the ideal gas behavior. So you've got this relationship. Okay, if pressure increases, volume decreases. Now this relationship does not hold true at all. It's only true at when does a gas behave ideally? Low temperatures or high temperatures?
High temperature and low pressure.
So high temperature and low pressure. So the gas will behave ideally at high temperature and low pressure. But if it's a non-ideal gas, I mean, what's a non-ideal gas? Non-ideal gas is one that has a lot of intermolecular forces. Like steam is going to be a very non-ideal gas because it's got hydrogen bonding. So non-ideal gas or non-ideal conditions. Which is that low temperature and high pressure. So this relationship is not going to be true. So how is it not going to be true? The first thing is that the actual pressure for any gas is always going to be lesser than the pressure that you obtain from the ideal gas equation. So whatever you get from PV0 NRT, you do your mathematics. The actual pressure that you use, that you're going to go there, use a pressure gauge to measure the actual pressure, it's going to come out to be slightly less. There's going to be an error in it. The more non-ideal the conditions, the bigger the difference. And the reason for that is that ideal gases assume that they don't have intermolecular forces, or gas particles don't have intermolecular forces. That's the assumption of an ideal gas, right? Real gases, they do have some intermolecular forces, especially under non-ideal conditions, and if it's a non-ideal gas. So what happens is that, what is pressure? Pressure is the force that the particles exert when they bump into the walls of the container. Now, ideal gas equation assumes that they don't attract each other. But what happens is that these particles are constantly attracting, or they have some intermolecular force. They might have van der Waals forces, they might have dipoles, they might have hydrogen bonding. So what happens is that the particles are attracting each other in reality. And if this particle is going to go and hit the container, the other particles are pulling it behind. I mean, they're all pulling this particle in the opposite direction. So the particle slows down. So your particle slows down, and hence less pressure is exerted. So do you get this point that your actual pressure is always going to be less than the one that's calculated by the equation? Is that clear?
Yes.
So what does that do to the value of PV? So if your P actual is coming out to be, let's call it P real. So let's call this P real. So if your actual pressure is coming out to be less, so your P into V product is going to be less than the one that's given by the equation. Is that clear? So if you use a pressure gauge to measure this, your actual value is going to come out to be slightly less. The more ideal the conditions, the closer these two are going to be. Your equation calculation and your actual measurements are going to be very close. The further you are from ideal conditions, or if you have a very non-ideal gas, the lesser it's going to be. So the point is that your P into V, the real P into V, is going to be less. Is that clear? So there's going to be a dip in your graph if you do actual measurements. So is this part clear? I mean, this part only. Is this clear?
Yes, it's clear.
Okay, so, and remember, the more the ideal conditions, the closer the green line is going to be to the red line. Okay, so it's going to start behaving ideally if you have ideal gas conditions. So then why does it rise up? The reason why it does rise up is if you increase pressure, what is this relationship? It says that if you increase pressure, the volume should decrease, right? So you imagine you're compressing a gas. And let me One second, if I can see it. Yeah, so imagine you are compressing a gas, right? So you keep on increasing pressure, the volume should go to zero, the volume should decrease. But the problem with gases is that real gases, because ideal gas assumes that the particles themselves have no volume or they have negligible volume. The ideal gas assumptions are that most of the gas is just empty spaces. The particles themselves have no volume. Now, what happens is that a gas is going to be compressible up to a certain point. At a certain point, it will not be compressible because then you will have particles, and the particles will know because once you have run out of gaps. I mean, this image shows that. So once you're out of gaps, the gas kind of becomes incompressible. So your relationship fails at very high pressures. It's going to obey the relationship up to a certain point, and then it will fail. Is that clear?
Yes.
So the thing is, where's the so the thing is, this relationship, pressure increases, volume should decrease. But this relationship fails at high pressures, especially very high pressures. You increase pressure, and the volume becomes constant. It does not decrease. The gas becomes incompressible. So previously it was coming out to be a constant, right? But now you're increasing pressure, the volume is constant, it increases, the value increases. Right? It was a constant because one was increasing, the other was decreasing, but now one is increasing, the other is constant. So your value will now increase. So at high pressures, P into V, because V becomes a constant and it increases. Okay, so just this thing. Is this clear?
Yes, I got it.
Okay, so I'm just going to make it. We just have to keep it simple. They're not going to ask you a very big question on this. They're just going to ask you why is there a dip, right? So because for the dip, you're going to explain that the actual gas has intermolecular forces, and so you just have to remember this part that the. Okay, so just this. So particles they slow down because of intermolecular forces, and less pressure is exerted in reality. So your P into V is actually lesser. Why does it increase? Because of this thing, that the gas becomes incompressible and the volume stays constant. So your P into V product increases, and therefore it goes up at very high pressure. It starts disobeying the ideal gas equation. And the other question that you're going to get on this is they might give you two gases, and so the closer you are to the red line, the more ideal the gas is. So this darker line is more ideal, and this one is less ideal. So they're going to give you questions on identifying which one is which gas. So for example, hydrogen gas is going to be very ideal because it's got less intermolecular forces. It's a small molecule. It only has van der Waals forces. And if you're given ammonia, then ammonia is going to be very non-ideal because it's got more intermolecular forces. So it's going to deviate a lot. Okay, so just remember this graph.
Okay, thank you.
Now moving on. Achha, now this question, the enthalpies of formation of your reactants and your products are all given. So how do you How do you find the enthalpy of this reaction?
Products minus reactants.
We are simply plot minus reaction. So find this out. What's the enthalpy of this reaction? The product is minus 808 minus the reactant, which is minus 206, minus the other reactant, which is minus 2 times 286.
I got it as minus 30.
Because that's T. You just make sure that no mistakes. I mean, people make a lot of silly mistakes doing this because of too many negative signs and too many additions and subtractions. Now we've got this reaction. Which statement is correct? Tell me which statement is correct in this.
First one is wrong. Hydrogen is not reduced.
Okay, fine. H is +1 on both sides.
Yes. And it's not oxidized either, so B is wrong.
Okay.
It's not a redox reaction.
Yeah. The oxidation states don't change. This is +6. This is still +6. Oxygen is -2, both sides. Okay. Which conditions would favor the formation of hydrogen? I mean, basically forward reaction.
So higher temperature and
Yeah.
the pressure would be the number of moles on the right hand side is more. So we need a lower pressure.
Okay, so you need a low pressure. Low pressure favors more gas moles side. You can make sure they're all gases. Okay. So that's fine. High temperature favors endothermic, which is the forward. Again, you've got the following concentration. So you're already given the equilibrium concentrations. Yeah. So you just have to find the value of Kc. So Kc is what? Product concentration divided by reactant concentration. So it's 0.6. That's your product. And squared. Divided by your reactant 0.2 times H2, which is 0.3 cube.
I got it as 66.7.
Yeah, that's fine. Let's see, you've got the next one. You've got maltase speeds up the reaction. Specificity is no longer really in your course, so but if you're taking bio, you should have some idea. Do you know what specificity is? We can just ignore this. We can ignore this. Move on to the next one. It's no longer in your course. Which description of bonding and acid-base nature of aluminum oxide is correct? Aluminum oxide, is it covalent or ionic?
It's ionic. And it's amphoteric.
And it's amphoteric. Okay, so it's C. You know, inorganic X and Y elements of the third period X and Y are individually heated in excess chlorine. Each product is purified and then separately added to water. So they're basically forming chlorides, right? Both solutions have a pH of less than 5. less than 5, so acidic basically. So whose chlorides are acidic?
Silicon and phosphorus.
Okay, because they both hydrolyze and they both form, they both form HCl, and silicon oxide or hydroxide is formed and phosphoric acid gets formed. As an ore contains magnesium carbonate and barium carbonate, a sample of the ore is dissolved in nitric acid. So how can the solution be processed into a magnesium compound and a separate barium compound? So he reacts it with nitric acid. So I think magnesium nitrate and because both of the carbonates are going to react, and barium nitrate. And remember, nitrates are very soluble. So how do you separate them into their respective compounds? They're mixed together.
We will add H2SO4 and it will form barium sulfate, which is a white precipitate. We can then filter it.
Okay, so barium sulfate and magnesium sulfate. And for sulfates, the top ones are soluble, while the bottom ones are not soluble. So you can filter them. So it's going to be C, right? And so when calcium and calcium hydride react separately with water, they produce a white solid and a colorless gas. The white solid is the same compound in each reaction. So what do you think the white solid is? The white solid when they react with water.
Calcium oxide.
Yeah, calcium oxide or hydroxide. So what? Yeah, it's the same compound, right?
Yes.
So probably going to be calcium hydroxide because oxide and hydroxide are the same thing, but I guess there's too much water, so it's going to form hydroxide, right? So the first one is definitely going to produce an H2 gas. What about the other, if we make an equation? The white compound is definitely calcium hydroxide. What do you think is left in this case? It's again H2, I guess.
It's hydrogen.
So I guess for this because this one is more like guesswork. Can't be O2 because O goes over there. We can check this one second. Okay, this was 15. Yeah, it's same. Okay, that was the only one that made sense. Now, sulfuric acid, this is for halides, right? Concentrated sulfuric acid is added to sodium chloride and HCl gets formed. And concentrated sulfuric acid is added to sodium iodide and iodine is formed. So which statement explains these observations? Like what? Why do they behave differently? This is an NaI.
Sulfuric acid is oxidizing agent.
Yeah, but in the first one, it's not behaving as an oxidizing agent.
It behaves as an acid.
Yeah, in the first one, it behaves as an acid because it gives its H2Cl and there's a displacement reaction. It forms HCl, and what's left is sodium and sulfate, right? Or NaHSO4 or Na2SO4. And you see misty white fumes of HCl. But in the second one, you do get a displacement reaction initially that H and I combine, and the Na and sulfate, they react. But then what happens is that the HI quickly gets oxidized. It ends up forming iodine and the sulfur gets reduced. It ends up forming sulfur dioxide or H2S or even sulfur itself and water. So why does that happen?
Because iodide are stronger reducing agents than fluoride.
Yeah, so it's B, right? Because you got Cl minus one, you got I minus one. Cl minus one does not like to lose electrons. It's a small atom. It likes to gain electrons. It likes to keep its electrons. It's strongly attracted to its electrons because it's less shielded. The electrons are closer to the nucleus. So in the first case, in the case of Cl, it remains Cl minus one. It does not lead to a redox reaction. While I minus one is a bigger atom, a very big atom, it's more shielded, so its outer electrons are not that attracted to it. So it easily loses the electron. So as soon as I minus one gets formed, the I minus one turns into I2, it loses the electron. So B is the right option. Okay, so it's more easily oxidized. The next one is you've got a question which is there are two equilibriums. Each equilibrium position lies well to the left, so it's extremely to the left. Now he says that silver iodide will not dissolve in aqueous ammonia. Silver chloride will dissolve in aqueous ammonia, and another equilibrium is found, which is this one. And he says that so this is silver dissolving or silver chloride dissolving. The position of this equilibrium lies to the right. So the first two were to the left. This one is to the right. What is the order of magnitude of these three equilibrium constants? First one, which one is the biggest?
The biggest would be the one to the right. K2, K3.
Okay, so it's to the right, so you got more products, right? So K3, right?
Yes.
K3 is the biggest. What about K1 and K2? I mean, they're the smallest, right? Because they're to the left.
Yes.
Now, between these two, which one is more to the right?
More to the right would be AGI, the K2.
No, AGI would be he says it does not dissolve in aqueous ammonia. So that means this does not dissolve. It does not dissolve. So it does, I mean, so that means it's not going to the right. While
Okay,
AgCl will dissolve, right?
yes.
So that means
It's more to the right.
yeah, so the first one is willing to dissolve, but the second one is absolutely not willing to dissolve. So that must be K1. So what's the order? K1 and then K2, right?
Yes, and
So,
then
so it's going to be
K1 is
yeah.
yes.
I said next one. Elements and the compounds are important as catalysts. In which process is a compound used rather than an element? Like which process involves a compound? That's
Contact process. Vanadium oxide.
yeah. This one is iron. Catalytic converters have platinum, palladium, or rhodium. Halogenation is nickel, and this is a compound V2O5. Anyway, so the next one, the gaseous products of heating a mixture of CaOH2 and H4Cl are passed through solid CaO. What's the gaseous product of these two things?
Ammonia gas for the ammonium salt.
Yeah, so it's basically yeah. So base when it reacts with an ammonium salt, then it's an acid-base reaction. The OH accept an H plus one, the NH4 acts as an acid. It loses an H plus one, and the OH ions they accept an H plus one and turn into water, right? And what's left is your salt. So that's calcium and chloride. So we're talking about ammonia gas, right? And ammonia gas is passed through solid calcium oxide. So I don't think the ammonia gas and calcium oxide have any reaction because they're both basic, right? So it's only to absorb water vapors, and a gas W is collected. I don't know why there's another gas being collected. So I said it's a pretty long question. So it says that W is collected. Why is there going to be W? I say, anyways, whatever happens, water gets removed in the process, and he says something W gets collected, right? W is oxidized by Cl2 to produce two gases, so you're getting two more gases now. So now you're getting what X and Y, and he says that W is now oxidized. X is the element, Y is acidic. Y reacts with W to, I mean, how can anyone keep track of this? Now he says that X is an element, Y is acidic. So Y is definitely, I said, there is no Y. Y reacts with W. What was W? Y reacts with?
Is W ammonia?
1 second. Y reacts with W to produce. What are X and Z? Yeah, W has to be ammonia, right?
Yeah, makes sense.
I mean, that's the only thing that makes sense. W has to be ammonia, right? And he says that W, which is ammonia, reacts with Y, which is acidic. So Y must be HCl then, I guess.
So it would form an ammonium salt. So it's NH4Cl.
Yes, it's going to be, I guess it's going to be B.
Yes.
Because over here, what happened was that the ammonia reacted with Cl2, and he said that W was oxidized. So I guess N2 and HCl will get produced. N is -3 and N is 0 now, right? So I mean that's the only possibility. You don't see O2 or calcium chloride forming anywhere. I mean calcium was never anywhere anyways. So I think we can complete the rest of the paper tomorrow. We can do one more question. This is question 20. How many chiral centers are present? Now we've got organic questions.
Carbon with the methyl branch, I think it's chiral.
Yeah, that's chiral. I mean, usually most of these junctions are chiral, where you've got.
It's 3, yeah.
Yeah, this one is not chiral because these two are exactly the same. Double bonds are not chiral. The rest will have, I mean, all the rest will have more than, they've got a couple of H's. This one has 3 H's, this one has 3 H's. The middle one has 2 of the same thing, so it's 3. And let's do just one more of that. If you've got HBr reacting, so what's the Markovnikov's rule? Where will the H get added and where will the Br get added?
The carbon with more hydrogens will get the H.
So in this case, the H gets bonded over here and the Br gets bonded over here, right? And in this case, the right one is the one that's got more H's. You get the H likes to bond with the carbon that's already with more H's. So this one had 2 H's, now it's got a third one. So which one is the correct formula for this? I guess it's Br has to be.
It's B.
It's this one, right?
D?
It is D, right? The BR is over here and the BR is over here, right?
Yes, it's the
ठीक है. चलिए, we'll continue tomorrow then, right? And we'll
okay.
try. It's gonna be the same time.
Okay, thank you.
Okay then. ठीक है. यार आवाज आ रही है?
जी सर।
और मैंने कहा वो पेपर 2 कैसा हुआ था?
सर ठीक हुआ, इतना कोई अच्छा नहीं हुआ था। उसके ऑर्गेनिक के थोड़े से थोड़ी गड़बड़ हुई, उसमें कुछ नहीं समझ आया था तो हम छोड़ते ट्रॉफी में 5-6 मिनट उसको मिल गए थे।
नहीं, मुश्किल आया था.
मुश्किल तो नहीं, इससे पेपर ठीक था। इतना बहुत ज़्यादा आसान भी नहीं था और बहुत ज़्यादा ही मुश्किल भी नहीं था, बस मीडियम था।
उसे प्रैक्टिकल में वो जो आखिरी क्वेश्चन था वो तो साउंड में तुक्के ही लगाए थे, लेकिन वो जो साउंड एनालिसिस वाला वो लेकिन हो गया था सारा.
इस टाइम की वजह से आखिरी 2-3 मार्क्स वाला एक था, वो मुझसे नहीं हुआ था। लेकिन वो जो ऑब्जर्वेशंस लिखी थी उसमें बाकी सारा करना था, वो होगा।
क्योंकि
एक तो
मेनली तो ऑब्जर्वेशन ही लिखनी थी ना, और तो एनालिसिस तो मेरे ख्याल से उस पर कुछ खास
जी जी, बस उसमें वो
टाइम.
मैं 2 बड़े टेबल्स दिए हुए थे, उसमें ऑब्जर्वेशंस करनी थी।
चलो ठीक है. चलो इसके ये आखिरी अब रह गया 40, इस पे ये इनऑर्गेनिक ऑर्गेनिक का तो रट्टा लगाओ ना. ठीक है.
इसमें अच्छा आ जाएगा तो आई थिंक, मतलब इसमें अगर बहुत अच्छा आ जाए तो पूरी ग्रेड हो जा सकती
हाँ हाँ, अभी टाइम भी है. ठीक है. चलो ठीक है. ओके.
है। ठीक है सर, थैंक यू। सर रोजाना